Okay, so the first thing I think we should do here, if you haven't put a column for days, I think that makes sense, but would be to get a picture of what's going on with the data. One of the things the book will really stress is that you you want to see the patterns that are going on instead of just blindly applying a test. And if we do see the data here, we can see that there's certainly some kind of increasing trend there, which there should be because this is total cases, so it can never go down unless they nullify some cases or something. But if we then try to just apply a linear trend line, you should notice that it doesn't really seem to fit. I mean, even if we get some reasonable r squared there, which 0.92 is a very high r squared, we also need to use our common sense logic of looking at this picture. And this is where the book talks about looking at the residual graph too. So here's what that residual graph for this looks like. And again, you can see that it's really that same curve. If you would take the trend line, flatten it to the x-axis, we would get this right here. What if we really do have a good fitting model here, a couple of things we should see are that the points should be randomly scattered, first of all, around this 0, that there should be roughly as many above the line as below the line, that the spread between them on the left side is the same as the spread between the points on the right side. And we really don't see any of that happening here. There's a clear trend where here the points are all above, here the points are all below. So it's pretty clear that a linear model is not the best fit for what's going on with the situation here. So if that's the case, what could we then go to? Well, one of the things we could do is, and some of you did this, so I think a lot of your predictions were basically you took the linear model and then you ran a linear regression, you used these coefficients here to get an equation, and then plugged in 27 for the day, which would be the day that I asked you to predict right here. So you might have done that all very well mathematically, but we want to move beyond that now and try to figure out how can we approach the case where our model isn't necessarily fitting the best. So the next step would be to consider different models, and with this trend line option, we do have the option of doing something exponential, which, as we saw in that video, the exponential would fit that first part pretty nicely. Polynomial, if we increase the degree, we're going to start to get a pretty good fit. However, the polynomial is making some assumptions here where it doesn't, I mean, it's got a huge r squared, 0.9991 would be a perfect, but this is really overfitting the data now. It's taking the few data points we have and matching it with a model that doesn't really make sense biologically, it doesn't make sense socially, and so this isn't the ideal option. And you can try a couple others here that aren't going to fit very well. This distinctive pattern, which the video talked about, is known as a logistic curve. I think a sigmoid curve is also another name. It took me a while to find a place to model that. If I pull these aside here, I eventually found a website that you can put in the data points and it models the best prediction logistic curve based on those. So it's doing the same thing as a linear, except here the model matches up with what we see scientifically of an exponential start and then some kind of carrying capacity or population limit. In this case, it wouldn't be the entire population limit, but there would have been maybe the limit with social distancing measures in place would be right up here, just under 9,000. The inflection point is the point where things start to change. In this case, according to this model, it would have been around this point. And And if we look at the residuals there, they're certainly not perfect. Beginning, something was happening there. There's a trend. But after that, it's fairly random. In other words, it is following a logistic regression fairly well, which would give a prediction of, let's see, the logistic curve prediction for the day I ask you to predict would be 7990. If we look at the actual values here, it was 7,755, 7869. So you can see, again, even the logistic model is off by a bit, but it is closer than this linear. And my guess is, as time goes on, the logistic curve will continue to be closer, although this is based on human decisions, things that are somewhat not necessarily going to fit to a perfect model. So it brings us to another point. If the number was 7990, notice that only falls within, wait, no. Oh yeah, 7990 was my prediction. 7869. Notice that 7869 only falls within 2 of our confidence intervals. If this is truly a 90% confidence interval, and this is based on our subjective idea here rather than a mathematical calculation, but we would expect 90% of these to at least contain that actual value, and only 2 of 8, so only 25% of our confidence intervals. And this is pretty common, that our subjective probability for confidence intervals is we're much more overconfident about our ability to predict a range. So when we do get into predicting specific mathematical confidence intervals, one of the reasons we do that is because our human tendency, our subjective tendency, is to be overconfident about where a data value will fall.